Okay, so this is the ratio test notes. You're going to go ahead and take these notes on notebook paper. So if you don't have notebook paper out, go ahead and get that out now. We're going to start with remembering something that you learned last year, factorial. This little exclamation point means factorial, and 5 factorial simply means 5 times 4 times 3 times 2 times 1. Okay, and any factorial you would do a similar way. You just do the integers decreasing by 1 all multiplied together. All right, now let me show you one other example of when you did factorial. When you did combinations and permutations, you might have kind of experimented with this without the calculator. And let's say you had something like 5 factorial over 4 factorial. You would simplify it, and you wouldn't have to write it all out. 5 times 4 times 3 times 2 times 1, and then same thing in the denominator. What you could actually do here, just to kind of shorten your amount of work, is shorten 5 factorial into 5 times 4 factorial. These two statements are the exact same. So then when I'm dividing by 4 factorial, I can see easily that the 4 factorials divide out, and you're left with a 5. This is going to happen anytime you'd have a number factorial divided by another number factorial. You can simplify it quite easily using this technique. Okay, so now let's go more general. So n factorial, okay, where n is just an integer, would be n times n minus 1 times n minus 2 times, and then you just keep on going, okay, until you got on down to 1. We have no idea what n is, so we just write, dot, dot, dot. Oopsies. So now let's simplify n plus 1 factorial over n factorial. We're going to use this in a minute. So if you're like, why are we going to do this? You'll see in just a minute. So n plus 1 factorial would be n plus 1 times n times n minus 1 and minus 2 and so on. So I'm going to stop there and write it as n factorial. So the whole thing is here, do you understand why n plus 1 factorial is n plus 1 times n factorial? This is, I did it up here with numbers, now I'm doing it in the general. You may have questions about that, and so bring those questions to class. All right, the denominator I'm going to leave as n factorial, and I can see clearly that these cancel out, and this simplifies to just n plus 1 with no factorial at all to worry about. Okay, the next one works out very similarly. N minus 1 factorial, this time this is the thing I'm going to leave alone. N minus 1 factorial, and in the denominator I'm going to expand the n factorial to n times n minus 1 factorial. It's all about just expanding the factorial enough so that you can get some cancellation, and this is now 1 over n, which is, again, is much easier to work with than the original statement. Okay, so let's see how this has to do with what we've done. You may want to pause this, and if you write slow so that you can write all this down. It says if an infinite series, we just talked about this in the last couple of lessons, if it has a sum, then this is called convergent, meaning that the sum converges to a particular number. If an infinite series does not have a sum, this is called divergent. This would imply either infinity or negative infinity, or that it bounces around between positive and negative infinity. But these two words you need to understand. Convergent has to do with a sum. Divergent is it does not have a sum. Okay, so looking at number 1, I can see that I'm multiplying the denominator by 3, or I could say, okay, this is geometric, and the r value here is 1/3. Now, since this r value is less than 1, remember we had this absolute value of r is less than 1, then we know that this is going to have a sum. So I can go ahead and write converge based on previous knowledge from our 11.3 unit. Okay, so just in general, you may want to write this down for geometric. If the absolute value is less than 1, it's going to converge every time, because that means it has a sum. But if the absolute value of r is greater than 1, then that means this series is going to continue to get really big, or also big but negatively. So that would be a diverge situation. Okay, we've kind of already talked about this, not with the two words, but in terms of does it have a sum or doesn't it. All right, so what type of series is this one? What's the pattern? Okay, so the pattern is that you're adding 6 each time. This is an arithmetic sequence. Okay, and your common difference we would say is 6. Okay, we use a D for this. We haven't done a whole lot with arithmetic, so I don't want to get too caught up on this, but just think logically. What is this? Does this have a sum? Does it not have a sum? Okay, 10 plus 6, it's not going to get big very quickly, but it will continue to grow larger and larger. It does not have a sum, therefore this is going to diverge. Now the rule about arithmetic sequences is nice. If it's arithmetic, meaning you're either adding or subtracting a number, it's going to diverge every time. There's no exceptions. Okay, if the series is not one of the two that we were kind of used to from last year, if it's something different, then we're going to use something called the ratio test. So this says if the series is neither arithmetic or geometric, then use the ratio test. So here's the ratio test. The sum of a sub n, okay, this sum exists or it converges if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. This is kind of like the sum being less than 1. That may be a way you remember it. And you're like, well, what does all this mean? Well, we'll unpack this in a minute when we do an example. But basically, if the next term, like a sub n minus 1 is the previous term, this would be the next term. If the next term over the term before it, okay, if the limit of that, meaning if that number is getting larger and larger and larger, you're not going to have a sum. But if, as we go out to really large values, if the next term is smaller than the previous term, then this will give us a ratio that's less than 1, and we're using absolute values so that we don't have to worry about positive and negative. So hopefully that sheds a little bit of light on it. This is something, though, that is kind of confusing because it's a lot of notation. All right, so diverge is going to be quite the opposite. This sum will not exist, or this will diverge, if at the limit as n approaches 0 of the absolute value of a sub n plus 1 over a sub n, if that is greater than 1, meaning that your terms are basically getting larger as you go out to infinity. Okay, and that should make sense. I don't know why it's not wanting to draw that in. There we go. Now, this test actually doesn't work all the time. This test is inconclusive if this limit equals 1. So it's possible that this limit could equal 1, and in reality it could be a converge situation or a diverge situation. You won't know. There are other tests. Today we're only learning about this ratio test. Okay, so for today, some of these we just won't be able to do. All right, so now an example to kind of explain what we're doing here. So we have an infinite sum, all right, and we have, it looks like it's a combination between geometric and then something to do with factorial, and what we're trying to do is figure out, does this sum exist? Okay, we're not necessarily finding the sum. We're just saying, does it exist? Does it converge? Does it diverge? All right, and then later on we use more with this. So what I want to first unpack is, what is a sub n? A sub n is this statement right here, always. Okay, so -1 to the power of n times 2 to the power of n over n factorial. Okay, another thing we need to figure out is, okay, well, what is the next term? What is a sub n plus 1? Really, all we're going to do is, everywhere there is an n, put an n plus 1. It's kind of like function notation. It's not any more complicated than this. Okay, so now we've clearly decided what is a sub n, what is a sub n plus 1. So now what we need to do is to do this limit. Remember, we're doing the limit as n approaches 0 of the absolute value of a sub n plus 1 over a sub n. And we're going to figure out, is this limit going to be greater than 0, less than 0, equal to 0? Okay, so let's go ahead and plug in our two statements. Now these are fractions, and we're going to have to divide them. But for right now, I'm just going to write everything the exact way it is. So the a sub n plus 1, which is the next term, we're going to write that in the numerator. Okay, And now all of that, so I really should extend this, all of that is going to be divided by a sub n. So negative 1 to the n power, 2 to the n power over n factorial. Now you have a fraction to deal with, okay? So the next thing we're going to write is just that. The limit as n approaches infinity of the absolute value. And some of you are so caught up on how weird this looks that you're not even catching that all I'm really doing is writing it down each time. I really haven't even done any algebra besides just plugging in what goes where. Okay, so that's the top term, and I'm going to multiply by the reciprocal of the denominator. And we're just going to simplify things one at a time. We're not going to do it all at one time. Now I will say that I think some of you are going to be able to go straight from here to here really soon. You're not going to have to write it this way, okay? And in fact, a lot of times I'm going to go straight from here to here. All right, I haven't really done any of the simplifying yet though. All right, but it's important that you understand how we get to here, because now we're going to do some algebra. All right, so if you notice, there are some things that go together. Like for instance, this goes with this 2 to the n plus 1 goes with the 2 to the n, and then this n plus 1 factorial goes with n factorial. Okay, so when I rewrite this now, I'm taking this first one very slow. Okay, I'm going to write everything kind of, we're going to just do one thing at a time basically. So if I have negative 1 to some power, this could be an odd number, it could be an even number, and I'm dividing by negative 1 to a power that's just one off from that, what will that become? Basically, off to the side, I'm going to kind of do a little bit of scratch work here. What will negative 1, you know what, I'm going to go ahead and do this in my problem, sorry. I'm going to go ahead and write it as negative 1 to the n plus 1 over negative 1 to the n. What will this become? That's off by a factor of negative 1. So this will simplify to negative 1. So it looked complicated, but it simplifies quite nicely. Okay, and we'll write that in a minute. All right, now let's do the 2 to the n plus 1 over 2. What will this simplify to? Okay, it's off by a factor of 2. So this is actually going to simplify to 2 over 1, and we're going to write all this in a minute. And then for this last one, I'm going to go ahead and start even writing it. The n plus 1 factorial down here, I'm going to write as n plus 1 times n factorial. This is what we did on the first page, and that's why we started with this, so that you can cancel like that. All right, so let's write what we have left, and I'm going to re-explain it. Okay, I already explained it once, I'm going to explain it again. So negative 1 to the n plus 1 divided by negative 1 to the n. This could be like negative 1 to the 11th divided by negative 1 to the 10th. No matter what, this right here will simplify to negative 1. Okay, so now we have a times. Now we have 2 to the n plus 1 divided by 2 to the n. Think of this as 2 to the 11th divided by 2 to the 10th. This is going to give you just 2. You can also think of it as subtracting your exponents. N plus 1 minus n, that will just give you a 2 to the 1. All right, and then I've already went on the first page how to do this. So this is 1 over n plus 1. All right, so this is going to simplify quite nicely to the limit as n approaches infinity of the absolute value of negative 2 over n plus 1. I've just simplified all of that. Okay, and again, I think some of you are not going to have to write out everything every time, and we'll get there as we go along. So now this is something that we've seen before. Okay, don't think so much about what this limit is. You don't have to actually find the limit, okay? But in this case, you can find the limit using what we did in the previous lesson. This limit is equal to 0, right? Okay, but what I'm mostly concerned about is the fact that that limit is less than 1. I can see clearly by plugging in infinity just as it is, this limit is going to be less than 1. And don't worry about negatives and positives. That's why we have the absolute value. So if this limit is less than 1, this is going to converge, and that's your final answer, and all the work supports it. Okay, the work has to be there. All right, let's try another example. Okay, so here we have the infinite sum. I know it's infinite because of infinity, and it looks a lot like the one we just did, but there are some differences. Okay, maybe some more terms. There's no -1 here, there's no factorial, but it kind of looks similar. Well, we're going to do this the same way. Okay, first I'm going to write down what the nth term is. That is n squared times n 3 to the n plus 1 power over 2 to the power of n. And the n plus 1 term would be n plus 1 squared times 3. Now if I'm putting in n plus 1 in for n, that's going to become n plus 2. All over 2 to the power of n plus 1. Alright, so remember we're doing, let me write an equal sign there, we're doing the limit as n approaches infinity of the absolute value of the n plus 1 term divided by the nth term. Okay, so I'm going to go straight into the division by multiplying by the reciprocal. Okay, and I think this is fine for you to do. Okay, so we're going to write the n plus 1 term. That's going to be n plus 1 squared times 3 to the n plus 2 over 2 to the n plus 1 power. And I'm dividing by this one. So I'm going to go into the multiply by reciprocal. Now this is the setup. Now we have to do the algebra of actually simplifying it. Okay? So this is now going to be the limit as n approaches 0. You have to keep writing this. You can't just leave this off. This is part of every single step. Alright, so what we need to do is we need to simplify n plus 1 squared over n squared. Now there is no real simple trick to this, okay? You need to just square n plus 1, alright? And that is going to be n squared plus 2n plus 1. And I'm going to put this over n squared. Okay, now we need to simplify this. Okay, 3 to the n plus 2 over 3 to the n plus 1. We did something very similar to this. Hopefully you're at least thinking about what that's going to be. And then now this last one. Very similar. 2 to the power of n over 2 to the power of n plus 1. And we don't have to deal with any factorials on this, which is nice. Okay, let's simplify this just a little bit further before we find the limit. Okay, I cannot simplify that any further than I have. You cannot cross out those n squareds. Okay, what is this going to become if you subtract? It's going to become 3, okay, or we could say 3 over 1. This one, on the other hand, is going to become 1 over 2 if you simplify that. N minus n plus 1, that's going to become a -1 exponent on the n, or a 1/2. Alright, and if you want, you could go ahead and even write this one more time. As n approaches, limit as n approaches infinity of 3. I'm not going to distribute this through. That's really not going to help me in any way. So I'm not going to do that. Now, if you remember about these problems where you had same degree, numerator and denominator, and you were taking the infinite limit, okay, we could divide everything by n squared, or you could just remember that this is the horizontal asymptote of the leading coefficients, which is 3/2. Again, it's not so important that I know that it's 3/2. What's important that is that I realize that it's greater than 1. And so this means that this thing is going to diverge, and that's your final answer, diverge. But the word alone isn't enough. You need all that work to prove that this is a diverging limit or diverging sum. Okay, let's do another one, number 5. So number 5 says we've got this infinite limit, okay? It looks a lot like the ones we've done before. Our a sub n term is -1 to the power of n square root of n over n plus 1. And our n plus 1 term is going to be -1 to the power of n plus 1, the square root of n plus 1. And down here, instead of n plus 1, it's going to be n plus 2 because we're adding 1. Okay, so our limit as n approaches infinity of absolute value of a sub n plus 1 divided by a sub n is going to be the limit as n approaches infinity of the absolute value of this whole thing divided by the general term. So when I say divided by this, I'm going to say multiply by the reciprocal. Okay, so let's think about what this means. Let's group our terms together so that when we simplify, we can just go one at a time. So when we simplify, we've got this divided by that. Okay, we've already seen this. This is just going to give us a -1. Okay. Next we have, or everything else that we have does not, it does not really matter. Okay, I mean, sorry, let me back up. It does not simplify, and the fact that it doesn't simplify doesn't matter. So I'm just going to go ahead and rewrite it nice and neat. I'm going to go ahead and write that term first. Let me ask you though one thing. I didn't mention this on the other one, but did it matter that I even wrote this -1? Look at what it's inside of. It's inside absolute value bars. So actually you can kind of ignore these -1 terms from the get-go, and that would be okay. All right. Or you can keep it in there. It's not going to affect your answer really one way or the other. All right, so let's think about this. Let's think about how we did this type of problem before, okay, when we had square roots. All right, we looked to see what the degree was, and if you think about it in terms of degree, it's basically 1.5 or 3/2, both in the numerator and in the denominator. The only difference in these two terms is this +1 here, and this has an extra 1 here. But those things become insignificant when you're talking about numbers approaching infinity. All right? This limit, not this expression, but the limit, if you remember we had some like this, you would do leading coefficient over leading coefficient, which is 1. And when the test tells you that the limit equals 1, then this test is inconclusive. All right, it's not inconclusive meaning anything besides that. It means that this test does not tell us whether this converges or diverges. And so that's all you write. We don't know. We would have to do more. It's not because of the -1. It's because the limit actually equals 1. Okay, let's do one more example. Okay, so here we have a lot of factorials. Okay, and in fact, I actually wrote this down wrong. There should not be a factorial there. Okay, still though a lot of factorials. All right, so the a sub n term becomes n factorial squared over 3n factorial. And the n plus 1 term becomes n plus 1 factorial, and then you can put other parentheses squared. And down here we have where we're adding 1. I want you to really pay attention to what I'm about to do, because we haven't seen this yet. When you're substituting an n plus 1 in for n, that doesn't just become 3n plus 1. Well, it does if n plus 1 is parentheses, okay? So you'd have to write those parentheses. Probably something that would be easier to write, though, would just be to write this as 3n plus 3, and it will become clearer when I get into this, and we're still taking this to the factorial. All right, so remember our limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to the limit as n approaches infinity of the absolute value of this term. Okay, so this is going to become n plus 1 factorial squared over 3n plus 3 factorial times the reciprocal 3n factorial over n factorial squared. Okay, so we've set it up. Now we just have to solve it. All right, one last thing before we start really crossing out stuff and all that. Let's think about what n plus 1 factorial squared is. It's n plus 1 factorial times n plus 1 factorial, right? And then this is just 3n plus 3 factorial. And over here, we have 3n factorial. And down here, I'm going to go ahead and write this as n factorial, n factorial. Okay, now we're ready to go. All right, so let's think about this. This is equal to the limit as n approaches infinity of, we're going to simplify this with this. So this is going to become n plus 1 times n factorial, and then same thing with this one, n plus 1 times n factorial over n factorial, so I can see some cancellation. Okay, times. Now I have all of this to simplify with this. Okay. The 3n factorial is not what I need to change. I'm going to leave that as 3n factorial. It's this. I have 3n plus 3, and I have to decrease by 1, so then that becomes 3n plus 2. Decrease by 1, that becomes 3n plus 1. Decrease by 1, and that becomes 3n factorial. And I can stop there because now I can cancel out here and here. So let's write what we have left and see if we can figure out what this limit is equal to, or at least if it's greater than or less than 1. So the limit as n approaches infinity. And up here I've got n plus 1 times n plus 1. You could have written that as n plus 1 squared, that's fine. And down here I have 3n plus 3, 3n plus 2 times 3n plus 1. Remember, when you're finding this infinite limit, you can do the dividing by n. You could also, this is all factored out, so that trick doesn't really work unless you want to multiply everything out. But think about the degrees. The degree of the numerator is 2, the degree of the denominator is 3. So if you were to plug in infinity, okay, you would have a much, much bigger denominator, okay? This limit is going to equal 0. Now, if you're not getting this step, then that means you didn't get the last lesson. So please ask questions in class. I know that you probably will have questions in class over this particular lesson, mostly with all the simplifying. So bring those questions to class, and we will discuss that. Okay.